A package P of mass m is attached to one end of a string of length 2a over 5. The other end of the string is attached to a fixed point O. The package hangs at rest vertically below O with the string taut and is then projected horizontally with a speed u, as shown in the diagram. When OP has turned through an angle theta and the string is still taut, the tension in the string is T. The package is modelled as a particle and the string as being light and inextensible. In part A, we want to show that T is equal to 3mg cos theta minus 2mg plus 5mu squared over 2a. So let's draw a diagram of when it's in a position such as this. So originally it was hanging at the point P. It has now turned through an angle theta so that it is at a point Q. The tension in the string here is T. The mass is m, so we've got weight mg acting this way. This angle will also be theta, and that means the component of the weight that acts that way is mg cos theta. Now we want to know something about distances as well, so if we draw a horizontal just there, this distance here, since the radius is 2a over 5, would be 2a over 5 cos theta, making the distance here that the object has risen through 2a over 5, take away 2a over 5 cos theta. So I think we have all of the initial setup that we need for the problem. The kinetic energy when we're at P, that's when it's projected with the speed of u, is going to be equal to the kinetic energy at Q plus the potential energy at Q. So this is a half mu squared. So let's say that it has a speed of v at Q. This will be a half mv squared. Then the potential energy is mg into the distance that it's risen. So 2a over 5, take away 2a over 5 cos theta. Now the thing that we introduced here was the v. So what we want to do is find an expression for the v squared. So my first step here would be to cancel the m's throughout. Then I'm going to multiply through by 2. So we get u squared equals v squared. I'm also going to factor 2a out of 5 out of the next thing. Now remember, I multiplied through by 2, so I've got 2g. Then we've got 2a over 5, and we've got 1 take away cos theta. And then we can rearrange that to make v squared equal to u squared take away 4ga on 5 plus 4ga on 5 cos theta. And we'll use that result in a moment. What we can do now is consider the tension. The tension, which we can see on our diagram just here, take away mg cos theta. So tension take away mg cos theta is going to be equal to mv squared over r. But in this case, we know the r is 2a on 5. So t is going to be equal to mg cos theta plus 5mv squared on 2a. And just remembering that we have our expression for v squared up here, which we're going to use, because remember v squared is, or v itself, is something that we introduced. So t is going to be equal to mg cos theta plus 5m over 2a, and now let's bring in the u squared minus 4ga over 5 plus 4ga over 5 cos theta. Expanding all of that out gives me mg cos theta plus 5mu squared over 2a. And that is part of what we're trying to show. So that's good news. Then we have take away with all the cancelling 2mg. And then with all the cancelling that we can do, and 2mg cos theta. And so we can put these together, giving us 3mg cos theta. Then we've got the minus the 2mg, and we'll put the 5mu squared over 2a last, and that is the expression that we were trying to show. So we're now given that P moves in a complete vertical circle with centre O. Find in terms of A and G the minimum possible value of U. Okay, so to complete circles, we're going to require t greater than 0 when theta equals pi. And we're after the minimum, so take t equal to 0. And if we take t equal to 0 and theta equal to pi and substitute them in here, we get 0 equals negative 3mg minus 2mg plus 5mu squared on 2a. We can rearrange that to give ourselves 5mu squared on 2a equals 5mg. And then u squared is going to be 2ag, and so u will be the square root of 2ag. Given that u is equal to 2 root ag, find in terms of g the magnitude of the acceleration of p at the instance when OP is horizontal. Now remember, we have t is equal to 3mg cos theta minus 2mg plus 5mu squared over 2a. And we're looking at the situation where it's horizontal, which means theta is pi by 2. And of course, we've got the root 2 root ag for the u. So we'll substitute that in. Now the cosine of pi by 2 is 0, so this term is going to disappear. So we've got negative 2mg plus 5m over 2a multiplied by 4ag. So we've got an a that can cancel, and the 2 can cancel with the 4, making that a 2. And that would give us that t is equal to negative 2mg plus 10mg, giving t is equal to 8mg. Now the particle has a mass of m. So that means that horizontally here it's going to have an 8g acceleration, and of course the acceleration due to gravity downwards is g. And so if we think about that as 8g and g, then the magnitude of the acceleration is just going to be Pythagoras. It is going to be root 8 squared plus 1 squared g, which is root 65g. Then finally, part D was, apart from including air resistance, suggest one way in which the model could be refined to make it more realistic. Well, we could take into account the weight of the string, because strings aren't really light. We could take into account that the string is unlikely to be inextensible. All strings to some degree are elastic, and the package is not a particle. So it's just one mark. You just need to get one of those things down.